Hello, organizers. It's such an honor to participate in the first international conference on sustainable energy and advanced material at Ouargla University. My name is Houssam, a PhD student at Ouargla University. My work is going to be on red-blue shifts of photons emitted by equatorial geodesic particle and Kerr-Newman black hole parameters. I will start my presentation with a brief introduction. Black holes, as we all know, are considered as natural laboratories for testing physical theories, in particular physical theories that combine both quantum and gravitational effects, like quantum gravity. After the detection of gravitational waves in 2016 and the images of black holes, April 2019, and the last March, the study of black holes is getting more interest and focus. From an astrophysical point of view, observations are suggesting the existence of a supermassive black hole at the center of many spiral galaxies, including ours. From a technical point of view, in general relativity, the no-hair theorem states that all black holes are uniquely characterized by only three numbers: the mass of the black hole m, the electric charge of the black hole q, and the angular momentum of the black hole g. Unlike, for example, planets or stars, that its characterization needs to know also the temperature, for example, of the star, the size of the star, the internal composition of the star, and so on. But for black holes, we only need those three parameters. Hence, we can categorize black holes into four types: the neutral static Schwarzschild black holes, which is the simplest case, then the charged non-rotating Reissner-Nordstrom black hole, the neutral but rotating Kerr black hole, and the most general case, the charged rotating Kerr-Newman black hole, which is the case of interest in our work. In recent work published in Physical Review in 2015, the Kerr black hole parameters M and G were investigated by applying relativistic stationary axis symmetric formalism to study black hole rotation curves of massive neutral test particles, MNTPs. In that work, published in Physical Review, expressions for the mass m, rotation parameter a, and the radius of the observer were obtained in terms of red-blue shifts of photons traveling along null geodesics and emitted by massive neutral test particles orbiting the black hole in a stable circular equatorial motion. So, the purpose of our work is to investigate the three parameters m, g, and q. That is, all of the three parameters for the most general case, the Kerr-Newman black hole, in terms of blue-red shifts of photons emitted by similar MNTPs. So, we will start, of course, by a review of the Kerr-Newman metric, and here are the component of the Kerr-Newman metric, and here are the most important, maybe, characteristic of this metric. Here is the horizon condition, and the Kerr metric, of course, possesses two Killing vectors and one Killing tensor, and we know from general relativity that each Killing tensor corresponds to a constant of motion, and hence we have those three constants of motion: the energy of the particle, the angular momentum of the particle, and the Cartan constant. So using these three constants of motion alongside with the equation of normalization for massive particles, this is the equation of normalization for massive particles, we obtain those four equations of motions. In a similar way, using the previous constants of motion and this normalization equation for photons, in this case, where k nu is the form momentum of the photon, we obtain those four equations of motion. Now, let's move to the general expression for redshift. In general relativity, for the frequency of a photon of form momentum k nu, measured by an observer with forward velocity u nu at point P, is given by this expression. So, between 2 points E and D, the frequency shift subjected by photon is given by this expression. We will use this expression, this general expression, but after imposing three restrictions. The first restriction is that the frequency shift of the photon, we will consider only frequency shift of photons emitted by massive neutral test particles in stable equatorial, which means that UR equals 0 and UR point equals 0, and equatorial means that theta equals pi over 2, U theta equals 0, and the Cartan constant equals 0. The second restriction is that we will consider only the kinematic part of the frequency, not the whole part, which also include the gravitational part. And the third restriction is that we will only consider the frequency shift of photons emitted by object orbiting either sides of the black hole. Relying on these three conditions, we will get the following maximum and minimum kinematic frequency shifts, which only depend on the for velocity u, the angular velocity of the detector ud, and the impact parameter given by this expression. So Z1 will turn out to be redshift, while Z2 will turn out to be blue shift after substituting the full expressions of U, omega, and B. And this is the explicit expression of the redshift. And in a similar way, this is the full explicit expression for the blue shift, where we can notice that they only depend on A, M, Q, the three parameters, and the radii of the detector and the emitter. And as expected, our theory must be compatible with previous theory, so if we substitute Q equals 0, the previous Kerr-Newman frequency shift expressions will reduce to those of Kerr black hole obtained by Ouargla and Newcomb in their paper. Moreover, if we substitute A equals 0, the previous Kerr-Newman frequency shifts expression will reduce to those of non-rotating charged Reissner-Nordstrom black hole. Moreover, if we use the fact that the impact parameter is the same at point E and D, that is at the emitter and detector point, we will get this equation for RD, which is a sixth order equation. So having measured the A, M, Q, and BE, we believe that we can determine the radius of the detector. That is the distance between the detector and the center of the black hole. If we further take this restriction or this condition for a far away detector that satisfies this condition and this condition, the expressions of the blue and redshift will get enormously simplified, as you can see. So now let's go. If we solve the last couple of equations for rotation parameter, we will get this expression that we do believe if the blue and redshift are measured, the charge is measured, and the radius of the emitter, we can determine the rotation parameter of the black hole. Now, let's go to the first conclusion. Expressions for the kinematic red-blue shifts of photons emitted by massive neutral test particles orbiting the Kerr-Newman, the most general case black hole, in stable circular equatorial motion were established. Expressions for red-blue shifts for Kerr black hole were easily deduced by putting Q equals 0, which means our theory is compatible with the previous ones. Expressions for red-blue shifts for Reissner-Nordstrom black holes were also easily deduced by putting the rotation parameter equals 0. In the case where omega d equals 0, the angular velocity of the detector equals 0, or the square of the charge equals this quantity, the kinematic red-blue shifts vanished. So we only have a gravitational redshift. And in the case where the detector is located far away from the source and satisfies this condition, and where the blue shift and redshift equals each other, then the radius of the emitter RE is very near to the black hole horizons. Thank you for listening very much indeed.